Hey folks, we just released the first properly public version of the graphical user interface for QuantumSavory, the quantum network simulator supported by the Center for Quantum Networks and a few other National Science Foundation projects. In this video, I'll present the tool and run you through how you can use it. As forewarning though, I will be assuming some familiarity with quantum networks, and I will be assuming some familiarity with QuantumSavory itself, the underlying library. I want to stress the library itself, in which you can write your own simulations as code, is much more powerful than what you can do in the graphical user interface. And you can familiarize yourself with the library both through our documentation and through the recent manuscript we have shared describing the toolkit we have built. So with that out of the way, let's focus on the graphical user interface. In simulations done with QuantumSavory, there are a few important baseline concepts. First is the notion of a node, and I can create a node here by pressing Alt and click, and in layout tools you can see a few more details for how to play with layout. So a node is can be a network node, a computing node, a module of a computer. It's a location where local classical decisions will be made by a controller. It will be a location to which you can send classical messages and from which you can send classical messages, and it's the location where qubits, rather quantum systems, will be stored and processed, and multiple nodes will be networked together. A node is implemented behind the scenes as a QuantumSavory register, and such a register has multiple slots that I can add by clicking on Add Slot. And a slot can be a qubit, can be another system, and importantly, to a slot you can also assign a background noise process to describe all the nasty things that the environment is doing to your quantum system. So now that you have nodes and slots on those nodes, you probably would want to define some edges. Over these edges, classical and quantum communication will be happening. And now the most important thing here is that the majority of logic and dynamics in the discrete event simulation representing the network will be handled through what we call protocols. Protocols are these composable Lego-like building blocks out of which you build the large-scale controllers, for which cause some interesting dynamics to emerge in the simulation. And protocols are mostly assigned to nodes, for instance, as a classical control routine acting on a given node, processing both quantum and classical messages, or on an edge, for instance, as some physical process used to generate entanglement. So we can add some protocols to node 3, for instance, and here's an example of a cutoff protocol. This is a protocol that detects that the qubit that has been established here is too old now, and it's probably not good enough due to noise, and it's just being deleted. And we have many other protocols that are pre-implemented, and in QuantumSavory proper, the software behind the scenes, you can implement your own protocols. And if you select a protocol, protocol constructor widget appears, in which you can configure many of the features of that protocol. Hovering over each field or each feature gives you details about what that feature represents. And there are many interesting or valuable protocols out of which we can build bigger systems, but I won't be going through them right now. For those out for the moment, suggest you consult our documentation or future videos that go through specific protocols in more detail. Okay, with that, let's look at protocols that are attached to an edge. One that will be coming very often is the entangler protocol, which generates entanglement between the nodes connected by the given edge. And you can configure many different things about the entanglement generator. Another frequently used protocol that you would attach to an edge would be the entanglement consumer. This is a protocol that, as the name suggests, consumes entanglement. It's a way to evaluate the results of your simulation, where you're probably trying to generate some resource between multiple nodes. And the entanglement consumer will be consuming that resource, recording its quality, and it will be something you can use down the line to study the performance of the simulation you're doing. And let's actually make a somewhat complete simulation. I'll delete this node. And as a note, we are drawing things on a map right now, but we're actually not going to use any of the map features. We're not going to use any of the automatically calculated distances or potential fiber lengths or anything like that for the moment. So here I have two nodes. Let's generate a few nodes here as, slots. Let's put a few slots on this node as well. Let's rename this to something slightly more elegant. Alice and Bob, each of them having 2 qubits. And no protocols running on the nodes themselves, and let's have only the entangler running on the edge between them for now. And let's run this for 10 time units and see what happens when you run this simulation. Very quickly, entanglement was generated. Oh, apologies. See what happened here? The dots, the filled-in dots, represent that the qubit now stores some information. It's not just an empty slot, it's actually something is stored on it. And I was expecting that I would be able to click on this qubit and I would have a pretty line showing that it's entangled to a qubit here. But if you look, here you see that these qubits are actually not entangled to anything. Why did this happen? Why didn't the simulation work? Well, notice that as I was playing around, I had still left this cutoff protocol node A. So this cutoff protocol, notice that the qubit here was growing old and it just deleted to free it up. We don't want the cutoff protocol to work right now, so I need to reset the simulation to be able to edit anything, and I delete the cutoff protocol. And now indeed I have two nodes that locally don't have any special logic running on them, and I just have the entangler protocol between them. And let's run this again. It ran for some number of time units, and if I click on this guy, I see that it's entangled with this qubit here now. If I click on this guy, same thing. Many of the objects defined here have various introspection tools that let you study what has happened. So let's go through some of them. Not all of them are fully implemented, but for instance, let's click on node A and let's look at the slot. Now the dot is filled in corresponding to the slot actually storing some information. And we have this show results button. By default it tries to present a plot, but for this actually we don't have a representation plot available yet. But we can look at the raw text-like representation, and we can see that on node 1 and node 2 we have stored this state. And in future versions we will also have a nice visualization. And we can also click on the entanglement protocol, the entangler protocol that we were using, and look at visualizations related to it. And here we can introspect, given the configuration that we gave it, the configuration that you can see here, what is the state being generated, what are the temporal dynamics, and so on. And again, for every single protocol, every single state, there will be some related visualizations. For instance, let's reset the simulation again and see what happens if we also add an entanglement consumer. This is a pretty contrived simulation. We are just having a entanglement generator and immediately an entanglement consumer. Usually we would have some repeater chain, and the entanglement consumer would be only between the first and last node, so that you can study the dynamics of the whole repeater chain. You won't have something as contrived as generate entanglement and consume entanglement. This won't lead to interesting results in dynamics, but let's just do it for the sake of an example. And let's run the simulation again, but this time with entanglement consumer running. And we see now that uh, these two dots are not filled in. It's because the entanglement consumer, well, consumed entanglement. And let's see again the visualizations. This is the visualization corresponding to the entanglement generator, and this is the visualization corresponding to the entanglement consumer. And for the entanglement consumer, you see here at the top at what time was entanglement consumed, what was the quality of the consumed entanglement. Because we don't have any noise in the system, the fidelity is equal to 1. And here we see the histogram of when entanglement is generated. And this histogram, we would expect it to mimic this success probability curve. So let's do the simulation for a bit longer to actually see that these curves do match. And yeah, after 1,000 time units and many more samples, we see that the curves are very similar. Although here the curve is in terms of time between successful heralds of entanglement, while here is number of attempts before success. And to map from one to the other, we'll need to know what's the attempt time that we can specify here. Okay, before we continue with a more sophisticated example, let's go through some of the tools that we have available here. I will reset the simulation again. So here we have the log of what is happening, and it's useful if you want to debug some problem. There's a capability to search through the log and so on, and you can see more detailed messaging if you expand each log entry. To each simulation, you can also add a detailed description in Markdown format. And that would be used to provide some information about your simulation. The next two tabs are fairly important for defining global variables and state variables. So what are these? Well, notice that in the constructor for the protocols, we have a lot of configuration options that we can modify. Well, imagine that you have a repeater chain of 10, 20 repeaters. It would be very frustrating if we want to modify some of the configuration to have to go through every single repeater and change the configuration value manually. This is where variables can come in. Instead of putting the success probability to 0.5 here and then having to modify it for every single one of the edges in the repeater chain, we can define a variable called prop for probability, for instance, of type float64 and a value of 0.5, and we can link that variable here. That way, whenever we want to change the value, instead of having to change it in every single location, we just make it linked in every single location and change it centrally from here to 0.6, for instance. And we have support for many different input types, including in particular, this would be of interest, the capability to represent a symbolic object, for instance, L0, logical 0, tensor product, logical 1. So this is literally a small computer algebra system that lets you write down a symbolic quantum state. Very useful when you want to describe initial states for systems rather quantum dynamics. For instance, for the entangler protocol, you might want to specify a pair state, the state that is being generated by that entangler protocol. Here you can encode a lot of the interesting noise that's happening in the system, in the link, and so on. And you can directly write it as a expression here. For instance, let's say a bell pair, tensor logical 0, tensor product logical 0 plus logical 1, tensor product logical 1 divided by square root of 2. And now this protocol will be generating uh, uh, correlated either both spins up or both spins down. That happens to be the default. We didn't need to fill this in. It's the one that happens by default, but you can imagine you might want to implement a different state here with some different noise parameters. The thing is, even if you have this capability, it would be kind of annoying to have to do this uh, from scratch if you have some really interesting, complicated model that you want to write down. That's where the states zoo come in. The state zoo of QuantumSavory is a small repository of important models of quantum states. For instance, a very common model for an entangled state is the Barrett-Koch-Bell pair, where you have a certain probabilistic process and there are losses in the fiber that are accounted for in that process. There is dark counts in the detector that are accounted for. Point being that you don't need to, from scratch, to write down the state for such a system. You just go to state zoo and you create, again, a global variable, but a global variable based on our repository of useful states. So now that we have state bk here as a variable, we can, instead of this handwritten model, we can just link this to the Barrett-Koch-Bell pair. And with that, that's what we have in terms of variables. Again, a very important concept that would simplify the manipulation of very large networks, where you don't want to manually change every single value in the definition of your protocols when you want to sweep a parameter. Instead, you can define these global variables, and in particular global variables that rely on our states repository, together with this nice visualization for what the state actually is. Then for the creation of larger networks, we also have these layout tools, where by default here you have the help for how layout works directly on the map, where you can define nodes, edges, and virtual edges, and also these more sophisticated helpers that let you create a large repeater chain, as we'll see shortly, a star network, or 2D and all-to-all connected networks. These help you generate interesting networks without having to hand draw the entire network. And lastly, I've been mentioning a couple of times how the underlying library, QuantumSavory, is much more powerful than this user interface, this graphical user interface. For sophisticated simulations, you probably would want to go straight into writing code and doing your analysis in a bespoke fashion in that code. But while we have a lot of documentation and a manuscript and also examples of various simulations in our code base, as a pedagogical tool, being able to convert this graphical simulation in a script as a starting point is also helpful. So that's the point of this tab here. It takes your simulation and it converts it into a script that you can then run independently from the graphical user interface. It imports the necessary libraries. It defines a few global variables, like the duration of the simulation that you can see here, for instance. It starts creating the registers, register A and register, let me refresh this, register A and register B, the variables that we discussed, the Barrett-Koch variable, and then it defines various protocols, and it runs the simulation. And at the bottom there are also a few commented out pieces of code for generating plots and introspection tools. Okay, that's the baseline for how to use the tool. So now let's go through an actual interesting example, something that's not as contrived as a single edge on which we're running entanglement and a tomography consumer at the same time. Let's make an actual repeater chain. So go here and we click on new. We'll just discard the changes. Test project repeater chain. Of note, nothing here is stored on the server. The entirety of these projects, let's see, the two projects that we just created, all of this is stored in the local browser storage. If you clear your cache, these simulations are lost. So make sure that if you want to save them, to export them locally for long-term storage. If you want to use our server, our public server that's running this tool, you can. We won't be storing the simulations you're running, and more importantly, as an open source tool, this is a tool that you can run yourself on your own computer without needing the web access to our default public service. So in this new repeater chain program, we'll actually specifically use the repeater chain generator, because that drastically simplifies the creation of the network. Instead of having to draw 10 different repeaters and add slots to each repeater and add protocols, we'll just make the initial node, the repeater node, and the final node, and we'll call them Alice, Bob, and repeater. And we'll configure them. Let's have just 3 slots on Alice and Bob, and for now let's keep them noiseless. For the repeater, let's add 5 slots, because why not? And now the important part is what protocols we'll have. And this is basically the template repeater that would be used by the repeater chain generator to create multiple repeaters. For the template repeater, let's add entanglement tracker and a swapper protocol. It's the swapper protocol that's particularly important. It will be detecting whether there are qubits that are entangled both with something on the left and with something on the right, and if that's the case, it will be performing a swap. And when it performs a swap, it will be sending classical messages to the left and to the right, so that the entanglement tracker will potentially update, when it receives such message, the belief, the local belief about who a given qubit is entangled to. Importantly, for the swapper protocol, we'll need to specify a few parameters, specifically these node L and node H parameters. I won't be going in deep detail on the specifics of the protocols. Again, our documentation and manuscript are better places to look for that, and we'll have future lectures on the topic as well. But for this simulation to work, we do need to understand the swapper protocol. So as I mentioned, the swapper protocol detects whether locally there is a qubit entangled with something, let's say, on the left and on the right. So we have this node L and node H function, predicate functions, that will be serving the purpose of deciding, of making this decision. So node L, or node low, will be a predicate function that checks what the qubit is entangled to, and if it's entangled to something in the appropriate direction, it would be marking that qubit as an appropriate for swap. So if we have all of our indices left to right in an increasing fashion, the predicate can be just a predefined function that checks that the index is smaller than the current index, meaning that the node we're entangled to is on the left. And then for another qubit, the node we're entangled to should have a bigger index, ID, and if it has a bigger index, it means that it's on the right. And when both of those predicates are fulfilled for 2 different qubits in a given register, those 2 qubits will be marked and the swap will be performed on those qubits. And we need to specify this in the template, because if we're making a ton of copies, we don't want to go in every single copy and manually edit it. And last thing, so let's see, we have the entanglement tracker, we have the swapper. The last thing is generating a template edge, and on that edge setting the entangler generating protocol, and I will keep it with its default settings. And finally, I can use the repeater chain generator. Pick the initial node, pick the final node, pick the repeater template, pick the edge template, and how many repeaters. And I'll also add a virtual edge between A and B where I can attach the tomography, the entanglement consumer. That will be used to evaluate the final result of the simulation. So when I click generate chain, the template edge and the template repeater will be deleted, and 5 more repeaters will be generated. We have this. I'll just move A and B a little bit towards the top. As a reminder, the map is not really used right now. It's just a pretty background. Nothing is set to physical dimensions. And hopefully this is sufficient. We have A, and then the final index is B, and each repeater will be checking for something entangled with an index beneath it and an index above it, and if that happens, a swap will be performed. So let's see whether this works. We ran the simulation for 1 second. Some qubits got entangled. Let's click on this one, for instance. Well, this didn't just get entangled, it must have gotten entangled to repeater 3, and then repeater 3 must have gotten entangled to repeater 4, and then a swap must have happened to repeater 3. Let's see, is that visible from the logs? No, we are not having any of the debug logs turned on right now, so none of this is visible. Well, let's run the simulation for much longer. Okay. A lot more logs generated, a lot more qubits generated, and this qubit is entangled here. This qubit is entangled all the way to B. This qubit is also entangled all the way to B. Well, let's click on the... Oh, I never added an entanglement consumer. So basically the simulation locked up at this point. If we run it for longer, nothing new is happening because I never added the entanglement consumer. So let's reset the simulation and add the entanglement consumer and run the simulation for another 100 seconds. Okay, and now if we look at entanglement, yeah, there's some entanglement end to end, there's entanglement that's still not fully swapped. And let's look at the entanglement consumer protocol. Nothing's consumed yet. Has it been not running for long enough? So what's the problem? Why is it not working? After pausing the recording for a second to look around, well, it seems that the repeaters do have entanglement tracker and swapper protocol, but something is missing from the end nodes. They also need the entanglement tracker. The entanglement tracker is the classical controller that gets a message from the swapper protocol saying, hey, I performed a swap on your neighbor, and now you should know that you're entangled to someone else, not to me anymore. Well, without those entanglement trackers, A and B don't know that a sequence of swaps has happened, and now A and B are entangled to each other. That classical knowledge was not available anywhere. And it's that classical knowledge that's necessary for the entanglement consumer to be able to consume the entanglement. And with that, let's actually run the simulation. And because I reset the system, it will take a second to compile. Same with showing the results. Okay, the first step of the simulation happened, and now it's continuing with the rest. You can see how everything evolves, and the consumer has consumed a few pieces of a few entangled pairs. Let's run the simulation for a little bit longer. And nothing will happen anymore in the simulation because let's see who these guys are entangled to. A is entangled here, this guy is entangled here, and this guy is entangled here. Notice who these are entangled to. Okay. And now the rest of the nodes are entangled to the left and to the left. So if no matter how much more we run the simulation, for this particular set of predicates for who gets entangled to whom, we're deadlocked. And that's the value of simulation like this. Naively, you might think that, hey, if we're just going to entangle ourselves to someone if we just need to check whether we're entangled to someone on the left and someone on the right, and then we perform the swap, naively you might think that that's enough. It will be always extending the link, but notice that it led to a situation in which repeater 5 is entangled in a bunch of its nodes to A, in a bunch of its slots to A, and in a bunch other slots to something to the left of it. There is no swap that repeater 5 can perform. There are better, more structured rules for how a sequence of swaps can happen that will permit this to finish end to end. But those we'll cover in a different video more focused on actual swapper protocols. Here we will stop this video with the general rules for how you set up a simulation, the graphical user interface, and come in for future lectures when we will discuss we'll use this graphical user interface to actually discuss interesting protocols and how you set them up to not end up with a deadlock after only 2 bell pairs were generated. Let's just do one last thing, reset the simulation and run it once again, just to see whether we'll be a little bit more lucky. Yeah, in the second simulation we had way more samples before deadlocking. We had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 successful entangled pairs being generated and consumed before we deadlocked. And let's see, what is the deadlock here? Let's see, repeater 4. Well, repeater 4 is in the same deadlock state which we had repeater 5 in the previous simulation. Anyway, with that, remember, run simulations so you detect issues like these deadlocks before you deploy, and come next time when we'll see how you can set up a more intelligent set of predicates that won't suffer this type of deadlocks.